Hey everybody, it's Beej with Lambda School. Today we're going to be talking about binary, decimal, and hex. These are different numbering systems that we use when writing software with computers. The goal today is to understand these numbering systems, decimal, binary, and hexadecimal, and be able to convert between them. And we'll be doing most of this coding in C, but the lessons here are generally applicable across all programming languages. So let's see what it means that computers use ones and zeros deep down, and what that means for us from a human perspective, learning about decimal numbers and so on. So before we start that, I want to talk a little bit about the idea that numbers have values. And when we're doing work in computers, we tend to be doing work on a value. And is that value binary, or is it hexadecimal, or is it decimal? It doesn't actually matter when we're doing math on it from our perspective. And this is an important clarification to keep in mind. In this example, we have 12 apples on this table, and we agree that no matter if we're writing this number as a decimal number or as a binary number or as a hexadecimal, we agree that the number of apples on the table is the same. So it's important to recognize that there is this value that exists as an absolute numeric value that represents, say, the number of apples on the table. And regardless of how we write it down, if we write 12 apples or 11000 apples in binary or C apples in hexadecimal, we are still talking about the same number of apples. You can kind of think of it like a different language almost. So keep that in mind as we're going through this. Now, another piece of terminology we'll talk about is number bases. So I want to put this out here up front because we need to have some terminology as we discuss these so we know which type of numbering system we're referring to. Now, there are as many number bases as there are numbers in the universe, which is a lot, but we're only actually interested in a few of them from a computer science standpoint. 3 of them we're actually interested in, and then a 4th that's a straggler that I'll talk a little bit about. So decimal is what we already know. We say that this is a base 10 numbering system. The base refers to the number of digits that we have at our disposal. And we have 10 of them, 0 through 9. Binary is the other numbering system that we've all heard about with computers, and it has 2 digits, 0 and 1, so it's base 2. And in case you didn't know what bit stood for, it's short for binary digit. We'll get more into that later. Hexadecimal is another really common numbering system in computers. It has 16 digits, so it's base 16. One of the happy coincidences we'll see later on is that it's really easy to convert from binary to hexadecimal because their bases are powers of 2. So we'll see that in a bit. You may have already seen hexadecimal show up if you've done any work with CSS on the web. CSS colors, you see the hash mark followed by 6 characters, 0 through 9, A through F, representing red, green, and blue. Those numbers are in hexadecimal. So there we go. We may have already seen some of that. Octal is base 8, and I will talk about that later. You shouldn't have to use it. And if I ever say hex, I mean hexadecimal. I'm just being short. So a little bit of terminology here. Some of this we've already said, but I want to clarify a few more things. A byte is 8 binary digits, so an 8-digit number in binary, or 8 bits we like to say. So you've probably heard of bytes. A byte is made up of 8 bits. And if we set all those bits to 1 and we convert that to decimal, we get a value of 255. That's just a good value to have memorized. That is the largest number that you can store in a byte. And that is also FF hex, which is the largest value you can store in a byte in hexadecimal. If you've done those CSS colors, you might remember that FF is as big as it gets, which means 255 is the biggest value you can use for red or green or blue, which means that those red, green, and blue values are actually stored in 1 byte each. Interestingly, nibble is a rarely used term. It means half a byte or 4 bits, but we'll use it a little bit for conversion. If you're doing networking, octet is often used instead of byte, means the same thing. So I said I was going to talk about octal, and this is it. Don't use it. Unless you really have to. There are certain rare cases where octal shows up, but the most common case is when people use it on accident when they didn't mean to. So in the C programming language and in a variety of other languages, if you put a leading 0 in front of a decimal number, that actually is telling the compiler that you mean it's an octal number. And the compiler will think, oh, 012 octal, I'll convert that into a value deep down, which happens to be equal to decimal value 10. And you as the programmer probably didn't mean that. So the trap is, if you put a leading 0 in front of a decimal number, it changes it into an octal number. Probably not what you meant, so don't do that. Anyway, without any further ado, let's see if we can get some conversions done here. And we'll try to convert from one thing to another. And we'll do this by hand at first, but then we'll write some C code that does the same thing. Often it's good to know how to do the conversion in your head, but most frequently people have the compiler do it for them instead. But let's actually, before we start this, let's do a little bit of counting so that I can demonstrate what these numbers mean here, the 128th place and the 64th place and so on. So let's start counting in base 10 in decimal, just like we always have done. And forgive me, this will be a review for everybody, but I want to show kind of what happens when we count up and we run out of digits with base 10, and then we have to add ourselves another digit, because we're going to do the same thing in binary. And we can use this to kind of make sense of binary numbers. So when we start counting in base 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we've run out of digits, right? Base 10 only has 10 digits. So what do you do when you run out of digits? You add another place. You add the tens place. And this is effectively saying, oh, hey, at this point, we have 110 and 0 ones. And then we keep counting, 110 and 1 1, 110 and 2 ones. And 110 and 2 ones, if you add it up, of course, that's 12, which is what we're used to seeing. But we want to do the exact same thing in binary now. So let's have a look at that. So base 2 binary, let's count up. I'm going to leave myself some space here. So we'll start at 0, and we'll go to 1, and I'm out of digits. So what do I have to do? Just like with decimal, I have to add another place. So we add a place right here. And we say, all right, here I said we had a 0, here I said we had a 1. Here I'm saying we have 1, 2, and 0 ones. So in binary, this becomes the twos place. We're used to it being the tens place in decimal, right? It goes tens, hundreds, thousands, and so on, because it's base 10. It follows powers of 10. 10 to the 0 is 1, 10 squared, or 10 to the 1 is 10, 10 squared is 100. Anyway, the same thing happens here, except instead of powers of 10, we're going to use powers of 2. So this is the twos place, and we can keep counting up. We get here, which is decimal 3, but we've run out of digits again, so we have to add another place. So we add the 4's place, and we say we have 1, 4, 0, 2s, and 0, 1s, and so this decimal value here is 4. And indeed it should be, because this 0, 1, 2, 3, 4 is how we're counting up. So the exact same thing happens. We run out of digits, we add another place. And so in binary, these places are the 1's place, the 2's, the 4's, the 8's, the 16's, the 32's, 64's, 128's, and it keeps on going. You might find it convenient as a developer to actually memorize them all the way up to, say, 2 to the 15th or 2 to the 16th. The numbers frequently pop up all over the place. You've seen like RAM sizes. You've got 2048 megabytes of RAM and so on like that. These are all powers of 2. So now that we've done some counting there, let's actually do some conversion. So I'm going to make up a number right here. Let's see. What do we have here? So this number is, we have a 1 here, and if I trace this up, I see that we are in the 64's place. So this is saying we have 164. We'd like to convert this to decimal, so I'm going to write that down. We got a 64. And then we don't have a 32, but we do have a 16. So I'll put that there. We don't have an 8 because 8 has a 0 there, but we do have a 4 and a 2. So that'll be 6. And let's see, can I do my math right? 60, 70, 80, does that come to 86? I'm pretty sure. Is that right? 64 plus 22, 86? Yeah. So that's 86 decimal. And that is totally 100% equivalent to this number in binary. I'm going to leave off this leading 0 here. 101. And let's see here. Let's go the other way. Now let's do another one of these. Let's do another one. Maybe a smaller one. I'll put just the number 1111 here. I'm leaving off the leading zeros here. So this is the 8's place, the 4's place, the 2's place, and the 1's place. And so again, we just have to add up those values. 8 plus 4 plus 2 plus 1, and that should be 15 decimal, which is equivalent to 1111 binary. So these values are the same. This is important to point out. If we had 15 apples on the table, that would be 15 apples decimal. That would be exactly the same as saying we have 1111 apples binary. Just a different language for the same value. Now, if we want to go the other direction, it can be a little bit trickier. So let's do some conversions from decimal to binary. Let's take a number like 67 decimal. What is this in binary? Well, there's no quick and easy way to do this, at least not mentally for me, but I do some observation and I say out of 128 and 64 and 32 and 16 and 8 and 4 and 2 and 1, what combination of those things added together gets me 67? Well, I think it's going to be 64 plus something, because 64 is pretty close to 67, but it's not over. So we need to find 3 more. 64 plus 3 is 67, but we don't have a 3. We've only got a 1's place, a 2's place, a 4's place, an 8's place. So we can use those. 64 plus 4 is too high, so let's go 64 plus 2. That gets me 66. We're almost there. I just need one more. Unfortunately, we do have the 1's place, so I can use the 1's place. And again, 64 and 2 and 1, they come out of here, the place values. And 64 plus 2 plus 1 is 67, which is the number we're after. And we can convert that to binary by putting a 1 for 64, 0 for 32, 0 for 16, 0 for 8, 0 for 4, 1 for 2, and 1 for 1. So we have a 64 and a 2 and a 1. And that's what we're saying right here. We have a 64, and we have a 2, and we have a 1. So this binary is equivalent to 67 decimal. So let's do one more, such as 33 decimal. What is it in binary? So what's the first thing we need to do? We need to go through our list of stuff up here and see which combination of these numbers adds together to become 33. 64 is too big. 16 is small enough, but you'd find that you might not be able to make any value out of 16, 8, 4, 2, and 1 that added to 33. 32 is, of course, the next smallest one from 33. So 33 equals 32 plus something. And now we need 32 plus 1, clearly. So we need to see if we have a 1 available here. And we do. So 32 plus 1. And we can do this now in binary by putting a 1 in the 32's place, 0 in the 16's place, 0 in the 8's place, 0 in the 4's place, 0 in the 2's place, and a 1 in the 1 place. So this binary is equivalent to 33 decimal. All right. So now that we've done some of that, let's do some hexadecimal conversion. Remember, hexadecimal is base 16, and we're going to go from binary to hex. And I said there was a trick in there that you could do this a little bit more easily because binary and hex both are bases that are powers of 2. But let's take a binary number and convert it into hex and see how that works. We're going to do that first by splitting it up into nibbles. If you remember, nibble is 4 bits, it's half a byte. So here is a 1 byte number. It is 8 bits long in binary, and we're going to split this into 2 pieces. So we're going to take this number and we're going to split it right in half into 2 nibbles. Now each of these nibbles can be converted individually into a hex digit, which is kind of cool. So this right nibble, we have to do a conversion from binary to hexadecimal. And it's probably easiest just to do it binary to decimal first. And if we end up with a number bigger than 9, then we can do some finger counting to figure out what the hex digit is. So this right number of 4 bits right here, just this in solitude, forgetting about the left-hand side, this is just 1, 1. That's all it is. It's got a 1 in the 1's place and a 1 in the 2's place. And so to convert it to decimal, we add 1 plus 2 gives us 3. So this right number is 3 in decimal. Turns out any number under 10 is the same in decimal and hexadecimal. So we can write 3 for hexadecimal here. What about this number right here? 1010. We can do addition again. Let's see, this is the 1's place, the 2's place, the 4's place, the 8's place. So we have 1 8 and 1 4. So this number, no, I'm sorry, like this doesn't add up. We have 1 8 and 1 2. So this number is 8 plus 2, it is 10, but 10 is 2 digits long. That's too big. That's also decimal. We want 10 in hexadecimal. But if you remember how hexadecimal counts up, it counts from 0 to 9, and then the next digit is A. So A in hexadecimal is the same as 10 decimal. And somewhere in the back of my brain, at some point, I've memorized that 1010, 1010 means hexadecimal A. So that's probably a good one to have memorized. And so then you put these 2 digits together, and we say the result is A3. So hexadecimal A3 is exactly equivalent to 10100011. So it's pretty neat how the byte splits in half, and you can take one hex digit from half the byte and another hex digit from the other. Let's do this in reverse now. I'll do it, you can follow along here. So let's take the hex digit C7 and let's convert it to binary. We're going to do this exact same procedure in reverse, right? We're going to split this in half. We're going to figure out which binary numbers correspond to these 2 numbers, and then we're going to cram those together into a single byte. So first of all, let's do C. C is a tougher one. So C in hex, what is that in decimal? I'm going to do some finger counting here. A is 10, B is 11, C is 12. All right, so C hex is 12 decimal. So now I want to convert that 12 decimal into binary. And so I need to figure out which combination, like we did before, which combination of these numbers adds up to 12. And it turns out 8 plus 4 adds to 12. And we don't, so we need 1 8 and 1 4 and no 2s and no 1s. So in binary, we're going to have 1 8, 1 4, 0 2s, and 0 1s. So there's our C. And then the other number we have is 7. And so we need to do the same thing. What combination of these numbers adds up to 7? And I see that 4 plus 2 is 6, plus 1 is 7. So we need 1, 4, 1, 2, and 1, 1, and no 8s. So 0 8s, 1, 4, 1, 2, and 1, 1. And then we can cram all these bits together, and we can say that C7 hex is the same as 1100, 0111 binary. If you want to convert from hex to decimal, or decimal to hex, that takes a little bit more mental gymnastics. You might find it easier to convert to binary as an intermediate form. And use that instead. Or, more practically speaking, you probably just use the computer to do the calculations. But I can safely say that software engineers do not regret knowing how to do these conversions mentally. It can be really useful if you're looking at a number to recognize a certain bit pattern in that number, no matter what the number base is. It might be a giveaway that something spectacular is occurring. For instance, if your program crashes and you see that a value is 256, you might recognize that that is 1 bit larger than a byte can hold, and maybe there was some kind of overflow or something like that. So, good to be able to do these conversions in your head. But let's go ahead and do some of these in C. So I've got sort of a basic outline of a C program here, and I want to write some numbers down in C, and I would also like to do some conversions between those numbers. So I'm going to declare an integer here, and I'm going to declare it to be 100. What is the value of that is a question I would have for you. How many apples are on the table? And your first thought is probably 100, and you would be right. But how do you know that that was 100 decimal that I wrote right there? How do you know that wasn't 100 binary, 100? How do you know it wasn't a 100 hexadecimal? Because these are all different numbers. So how would we know the difference? It turns out we have to hint. We have to tell the compiler what the number base is. If we don't actually say anything about it, and we say 100, then great, it's just decimal. Just like we're used to from grade school. But if we want to specify a hexadecimal number, we do so by putting a leading 0x in front of it. And so if I want to say hexadecimal 100, which of course is a different number, I can specify out here, this the value is 100 decimal, as we might expect, but here the value is 256 decimal. But the 0x tells the compiler, hey, that 100, that's not decimal anymore, that's a hex 100, just so you know. Likewise, there's a similar thing here, binary 100. Of course, we just did a bunch of conversions. This would be 1, 2, 4. So this value is 4 decimal. So this lets the compiler know that 100, we meant that as a binary value, a binary number. 0b, I should add, is not standard C, but it's an extension that a lot of C compilers have. All right, so if we wanted to write a value of 47F in hex, what do we have to do? That, yes, but it's hexadecimal. We have to tell the compiler, hey, that's hex. So there we go. That's how we do that. So now let's actually do some of those conversions. We are going to convert from a value into a string. This is kind of an interesting thing because, like I said, with the apples example, we have apples on the table, a certain number of apples, and that number of apples is the same regardless of how we write it down, which number base we use. So it's important to know that the number base really only matters when we write the number down, like when we print it out on the screen or we write it down in source code. The value deep down is going to be how math is done. Sure, we might write it in binary or we might write it in hex, but when we do comparisons and things like that, the value is used for the comparison. So this will compare true. Even though we didn't write b equals 4 up here, we wrote b as assigned binary 100, the value is 4. And so this comparison will be true. Just as if we'd written this comparison would be true. Just as if we'd written this, the comparison would be true. It's the value that's being used deep down. So keep that in mind as we do these conversions. So let's add some code here to take a binary number and print it out as hexadecimal. And this is 1 byte's worth of number right here. And I'm going to print that out as hex. Turns out printf has a format specifier for printing out numbers. We already know %d. This will print it out as a decimal number. We've already seen that, right? And I'm not sure what that decimal number is, but let's print it out. We'll print it out by saying is this value in binary is this value in decimal. So, oh, I can't do %s. Sorry about that. We're just going to do %d for decimal. So that should print out that in decimal, but if we want to print it in hex, there's another special format specifier, %x. So this will print it out as a hex number. If you give it a capital X, it'll print it out with the letter portions of the hex number capitalized. So if there's any A through F, it'll be capitalized instead of lowercase like it'll be in this case. So we can give this a shot, and we see that that number is 197 decimal, and it's C5 hex. And you can see in one case we have a lowercase c, in one case we have an uppercase c, depending on whether or not we use lowercase x or uppercase x here. So let's do another one. I'll do this one slightly differently. What we'll do in this case is we will try having a value of 255. This is a plain old decimal value. And I'm going to print this out in hex. I'll print it out with capitals. And so what's going to be the output of this? What do you think? Place your bets. 255 is an interesting number. If you know your powers of 2, you know that 256 is a power of 2. And 255 is 256 minus 1. And if you know how bit patterns work, you'd realize that 255 is a number, a byte full of all 1 bits. Every bit is turned on. And if you do a quick bit of mental gymnastics with 2 nibbles next to each other where every bit is turned on, and convert that into hexadecimal, you might be able to figure out what this is going to print ahead of time. Hit pause if you want to try it, because here goes the answer. FF. Yep, that's the maximum number that goes in a byte. If you want to store this result in a string, we can also do this in C. We can make room, a string that's big enough to do it. We can use sprintf to print into a string, and we can print the value into there. And then we can print that out. I'll just print that out using regular printf. Same result there. I'm sorry, I've got 2 new lines because I've left an extra new line in my sprintf. So this is a way you can convert that into a string if you need to print it out. So here we are converting. We've converted from binary to hex. We've converted from decimal to hex. Well, in short, what we've done is we've taken values and we've converted them into hex and printed them out. Unfortunately, there's no built-in way to convert to binary and print it out. You'd think that it would be really useful to just have a %b or some such but clearly that is not something that has happened. But we will leave it as an exercise to the reader to write a program that prints out a value in binary. It's a fun little challenge. So what about the other way? What if we have a string? Like here I am converting it to a string, but what if we have a string already and we wish to convert that to a number? So if I have a string such as 110011, and this is a binary number, and I wish to convert that into a value, I'm going to store that in a long instead of an int because of the function we're about to use. I want to store this in a value. There is a built-in function that is part of standard lib.h. It's called string to long. And this takes a few parameters. The first one is the string you wish to convert. The second one, I'll let you look up later. That lets you know if there were any bad characters encountered in the conversion, some errors. But if you put null there, those errors are ignored, and conversion stops as soon as it can no longer convert characters over. And then the last number is the base. This is binary. Remember, binary is base 2. So we're telling it which base we wish to convert. If we use base 10, of course, this number is 110,011. But we're using base 2, and this number is something in base 2. So now that we have that converted, we can just go ahead and print it out and see what that result is. And I've made an error here. This should be a %LD because it is a long. So because I've got extra warnings turned on, it told me that I was using the wrong format specifier for printf. All right, so now we see that this is 51, which it kind of looks like 32 plus 16 plus 3. That seems like 51. So we can also do the same thing with hex numbers, or actually any base you want, but hex and binary are what we'll use frequently. So let's do another one, char s2, and I'll put a hex number in here like f8. And we wish to do a conversion for that. So what do we do for that? It's probably going to be pretty similar to the base 2 conversion, right? I'll make a new value here, and I'll convert from string 2, don't care about the errors, base 2. Base 2? Base 2? Wait a minute, hex is base 16. We better tell it. Base 16. All right. And then let's print this guy out. Remember to use %LD this time because it's a long, and we'll print out value 2. Oh boy, all kinds of crazy stuff. Be sure that your strings are char pointers, not chars, because that'll make all kinds of trouble. And there we go. So F8 hex is 248 decimal because we're printing it out as a decimal number. So use strt along to convert strings into values that you can use to do math, and use sprintf to convert values into strings that you can use to print out. Now, what I'll leave you with here is a challenge. Go ahead and pause the screen if you want to get through it. But some counting, some binary and decimal conversions, and then lastly, the fun part, write a little program that outputs a value in binary. So if you have a C program that says int x equals 20 decimal, write a program, write a function that will take that and print it out as ones and zeros in binary. There's a hint there. You might want to look up the right shift operator and the bitwise and with ampersand. These can help you out. If you don't want to use those for some reason, divide and mod can also help. But those will be more fun. All right, everybody have a fun time.